When we talk about random variables, it's helpful to know what the expected value or mean is because it shows us where the random variable is centered. However, it doesn't tell us anything really about the distribution of the random variable. A random variable could have a really tight distribution or a really broad distribution and still be centered at that same expected value. So in order to know if it has a super tight distribution or a super spread out distribution, we consider the variance and the standard deviation of that random variable. So that's what we're going to talk about today, is how to find the variance and the standard deviation. So we have this definition that if we have a random variable with probability distribution f of x and mean mu, then the variance, or the expected variance, for that random variable is a sum for a discrete random variable and an integral for a continuous random variable, both taking the difference between the value of the random variable and the mean, squaring that, and multiplying it times the value of the probability distribution at that point. Now, when we take the positive square root of that variance, it's called the standard deviation. Working with this definition can be a little bit unwieldy, and it's a lot of arithmetic and a lot of calculations. Luckily, we have a theorem that tells us that the variance of a random variable is actually equal to the expected value of the random variable squared minus the mean squared. This simplifies it a lot, and we can use this theorem to calculate the variance in fewer steps. So here's an example with a discrete random variable. So the random variable can take on the values 0, 1, 2, or 3, and the probability distribution is given in this chart. Now, if we use the theorem to calculate our variance, then we have our variance equals the expected value of our random variable squared minus our mean squared. So in order to use the theorem, we need to calculate both the mean and the expected value of our random variable squared. So to calculate the mean, we're going to take our value x, and we're going to multiply it by the value of the probability distribution at that point. So 0.51 for 0. And we're going to add to that the next value that our random variable can take, 1, times the probability distribution value at that point, so 0.38. And we're going to continue this until we've done this for all of the values that our random variable can take. And then we find those products and the sum of the products, and we find that our mean is actually 0.61. Now we can find the expected value of our random variable squared by squaring the values, so we have 0 squared, and multiplying by our probability distribution value at that point. So we have 0 squared times 0.51, plus we have 1 squared times 0.38, plus we have 2 squared times 0.1, plus 3 squared times 0.01. So we're going to square all these values. I'll have 0, 1, 4, and 9, and then I'll be taking products with those and the sum of the products, and I'll find that I have 0.87 as the expected value of my random variable squared. So if I want to find my variance, I'm going to take the expected value of my random variable squared, so 0.87, and I'm going to subtract from that my mean, 0.61, squared. So I'll have 0.87 minus 0.61 squared, and when I square it and take that difference, I'll find that I have a variance of 0.4979. And there's my variance using the theorem. Here I have an example with a continuous random variable x, where my probability distribution is going to equal 2 times x minus 1 when 1 is less than x is less than 2, and it's going to be 0 elsewhere. So again, if I want to find my variance, remember our variance equals the expected value of our random variable squared minus our mean squared. So we need to find both our mean and the expected value of our random variable squared. So to find the mean, we take the integral of x times f of x dx, and we're taking this from negative infinity to infinity, but in this case that's equivalent to 1 to 2 because it'll be 0 everywhere else. So this is going to be the integral from 1 to 2 of x times 2 times x minus 1 dx. And I can bring that constant of 2 out and distribute the x. So this is really going to be 2 times the integral from 1 to 2 of x squared minus x dx. Now, when I integrate and do my substitutions and distribute my 2, I'm going to find this is actually equal to 5/3. Now, to find the expected value of my random variable squared, I'm going to be taking the integral, again from negative infinity to infinity, which is the equivalent of 1 to 2 here, since it's 0 everywhere else. And instead of using x, I'm going to be using x squared, f of x dx. And so when I do this, I'll actually be taking 2 times the integral from 1 to 2 of x cubed minus x squared dx. And after I integrate and do my substitutions and distribute my 2, I'll find that this is 17/6. Now all I have to do is plug these things into my variance equation. So I have my variance is going to equal my expected value of my random variable squared, so 17/6 minus my mean of 5/3 squared. So after I do this and do my subtraction and some simplification, I'm going to find that this is actually equal to 1/18. And that's going to be the variance of this continuous random variable. Now, sometimes we have a random variable that depends on another random variable. So say we have a random variable g of x that depends on our random variable x. And our random variable x has probability distribution f of x. If we want to know the variance of the random variable g of x, then we're going to take the sum over all the possible values of x for our random variable capital X, taking the difference between our g of x value and the mean of g of x and squaring that and multiplying times f of x whenever we have a discrete random variable x. Now, if x is a continuous random variable, then we're going to be integrating with respect to x, that same difference squared times the value of our probability distribution at the point x. This should look fairly similar to finding the expected value of a random variable that depends on another random variable in respect to how we treat g of x versus x, and the two interrelate. Now, when we have a joint probability distribution with two random variables, x and y, instead of talking about the variance, we talk about the covariance of x and y. And we calculate this by taking the sum over all the possible values of x and the sum over all the possible values of y of the product of the differences of x and the mean of x and y and the mean of y, all multiplied times the joint probability distribution value at the point x, y. Similarly, if our random variables are continuous, we're going to integrate over both x and y, that same product. Again, this definition looks a little bit unwieldy, so luckily we have a theorem to help us out. So that theorem tells us that the covariance of two random variables x and y with means mu sub x and mu sub y, respectively, is given by the expected value of the product of the two random variables minus the product of the means of those two random variables. So here we have an example. If we want to find the covariance of our random variables x and y that are given here with their joint probability distribution for these discrete random variables. Now the expected value of the product of x and y is given by x times y times the value of the joint probability distribution for each possible pairing of x and y, all added together. So I'll have 0 times 0 times 3/28, and I'll end up noticing that anytime x or y is going to be 0, then the product is going to be 0. So really, finding this, I'm going to have 0 for my first entry here, plus 0 for my second column, still first row, plus 0 for my third column, first row, plus a 0 for my first column, second row, this time because x is 0 instead of what y was 0 for the others. Then I'll actually have 1 times 1 times 3/14 plus 0 plus 0 times all of that stuff, so another 0, plus more zeros, so 2 more zeros. So I actually have the expected value of the product of x and y is 3/14. Now to find the mean of the random variable x, I'm going to be taking the sum over all the x values, so x goes from 0 to 2, of x g of x. So when I do this, when x is 0, I have a g of x value of 5/14, plus when x is 1, I have a g of x value of 15/28, plus when x is 2, I have a g of x value of 3/28. So when I take those products and that sum, I'll end up with a mean of 3/4 with respect to my random variable x. Now, if I take my random variable y to find the mean there, I'm going to be taking the sum over all the y values, so from 0 to 2, of y h of y. So when y is 0, h of y is 15/28. When y is 1, h of y is 3/7. And when y is 2, h of y is 1/28. So when I take those products and then that sum, I end up with a mean of 1/2 for my random variable y. So now I just use the theorem and plug stuff in. I have my covariance, xy, is going to equal the expected value I calculated, so my 3/14, minus the product of my mean with respect to x, so 3/4 times 1/2. And so I'll take this product here, and then I'll take the difference, and I'll find a difference of -9/56. So my covariance is -9/56. And I would do the same exact thing in an example with a continuous variable, except for instead of taking sums, I would be taking integrals instead. Now, When we're interested in the strength of a relationship between two random variables x and y, our covariance doesn't actually necessarily tell us anything because it depends on the units that x and y are measured in. If we want to know something about the strength of the relationship between them, we need to have something that doesn't have a scale attached to it. We need to have something that doesn't have a scale attached to it. In other words, it doesn't depend on the units that are used to measure x and y. So what we use is called the correlation coefficient. So the correlation coefficient takes the covariance and divides it by the product of the standard deviations. So what this is going to do is give us a value between -1 and 1. Now, a value of about 0 is telling us that the two random variables aren't really related to each other at all. And a value of -1 is going to tell us they are related to each other in a sort of opposite fashion. And one closer to 1 is going to tell us that they are more directly related to one another.